In this lesson, we're going to take a look at ion size and ionization energy. So first, let's remember what an ion is. Ions are merely charged atoms. They become charged by gaining or losing electrons. So the number of protons does not equal the number of electrons. Cations, remember, are positive because they've lost electrons, so they have more protons than electrons. Anions are negative because they have gained electrons. Now, if you think about orbitals on that, this will make sense for metals to form cations and nonmetals to form anions. If you put that together with the Octet Rule, remember the Octet Rule says atoms tend to be stable when their valence S&P orbitals are full. So we'll look at that in more detail later, but for now, metals tend to form cations, nonmetals anions, which this table shows. It shows me ions across the periodic table, so you can see everything in column 1 is a 1+ ion, and that's because everything in column 1 has an S electron in its valence shell, and eliminating that electron makes it look like the previous noble gas, which makes it have its S&P orbitals full. And you can see as we move down, just like before, the ions get larger. Now, the Ionic Radius is just the gray circle in the middle. The colors behind these are to let us know what we're looking at. The blue ones are metals, the yellow ones are metalloids or semi-metallics, and the gray ones are our non-metals. Now, as we move across in the metals tend to increase in charge. So from lithium as a 1+ to beryllium as a 2+, sodium is a 1+, magnesium is a 2+, aluminum is a 3+. That trend sort of breaks down in the transition metals because remember you've got the d orbitals there, and so you've got electrons that are filling in not necessarily in p or d orbital order because they're going lowest energy. Now, as the ion becomes more positive, that means there is a greater number of protons than electrons, so the nucleus is able to pull the electrons in closer, and there's less repulsion between electrons because there are simply less negative charges. So within a row, the more positive the ion, the smaller the ion is going to be. The negative thing, that trend still holds. The more positive it is, the smaller it's going to be. Well, -1 is a lot more positive than -3, so the more negative it is, the larger it is because there's more electrons present. The electrons will repel each other more, which means the atom will expand a little bit, and there's not any more protons to help hold those electrons together. So the more negative it is within a row, the larger it tends to be. The more positive within a row, the smaller it tends to be. And then moving down the periodic table, of course, gets us larger ions because those electrons are in higher shells. So that's all summarized here. Going down a group, if the ion charge stays the same, the size increases because we're putting electrons into a higher shell. Going across the period, the ion size depends on charge. The smallest ions are the most positive, because it allows the protons to attract it closer. The largest ions are the most negative because the electrons repel each other more. And so then we get into this idea of how do ions actually form? Well, ions form by having electrons removed from them or added to them. Now, for now, we're looking at ionization energy. And ionization energy is the amount of energy needed to remove an electron from an atom. There is the idea of electron affinity, which is the energy requirement to absorb or release an electron. We're not really going to look at that, but we are going to look at ionization energy. So the amount of energy needed to remove an electron from an atom. Like this says, usually measured in joules or kilojoules per mole. And the higher the energy, the more difficult it is to remove an electron. Basically, if it takes more energy to remove the electron, it takes more work. So there's more work input to remove this electron. It's harder to do that. Now, this graph shows us ionization energy in kilojoules per mole for the first 92 elements. And you can see hydrogen is here at around 1300 kilojoules per mole, and helium is up here. Helium is much harder to ionize. It takes a lot more energy. And if we come down, this is the boron electron configuration, but helium would just be this, right? 1s with 2. Well, hydrogen, moving one electron, actually makes it just a proton, and it's a lower energy because it just empties an orbital. But helium, we have this nice symmetric full orbital, and so taking that one electron away requires a little bit more energy because it leaves us with an unstable, unfilled s orbital. Then we go to lithium, and lithium has low energy because lithium would just have 1s2, 2s1, right? And so if I remove this just one electron, it drops down and it looks like 1s, and that's a stable full shell, right? And then we have beryllium up here. It's harder to take away this second electron because taking that electron away destabilizes this 2s orbital. It's not full anymore. And then we have this trend where boron shows up, and boron is a little bit easier to ionize than beryllium. But if you think about it in its orbital notation here, that's because boron has this one extra electron in the p orbitals. And so if we pull that away, it takes some work, but it also gives us a full s orbital, which is fairly stable. So it's less energetic to remove this 1p, or this one electron from the p orbital, than it is to remove this electron from the 2s because of the configuration that it leaves us with. And then we see the trend where, okay, so we've gone boron, carbon, nitrogen gets us to here. So here's nitrogen. We've got all three of these. So the energy's been steadily increasing to make these ions. And then we have oxygen, and oxygen drops back down again. It's a little bit easier to ionize oxygen than it is to ionize nitrogen, even though it's further right on the table. And that again gets back to this configuration. To ionize oxygen, the last electron that we're going to pull off, or the electron we pull off is the last one added, and that's this one in the p. And by pulling that one out, we have that little help because those electrons are repelling each other. So we are getting one electron, which is a favorable energy condition in each orbital again. So every time you see this little trend where in general across a period it's going up, the ionization energy is going up, but we do see the occasional down bump. That's because of the way the electrons are filling the orbitals. So we can explain those based on the electron configuration. So the general trend is across a period the ionization energy increases, but when we have the orbitals, when we have electrons starting to pair in orbitals, we tend to get a little bump that says, oh, well, this one was a little bit easier. Okay, so you can see these trends across the periodic table, and you can find your alkali metals. They're labeled here, but they're the ones that have the lowest ionization energy. They're the ones that are easiest to ionize. They're the ones that are easiest to pull electrons off of. You can also find your noble gases. They are up here at the top. Noble gases are hard to pull electrons off of. Remember, they have a full p orbital, right? So neon would be over here. We'd have an electron here and an electron here, and pulling an electron out of there is very, very difficult because we have a full s and p orbital, and so that's a very stable configuration. Now, so in general, going down a group, ionization energy decreases, and that's because you're further from the nucleus. Remember, we're in a higher shell, so it's easier to pull that electron off. And then the second trend we see here is going across a period. Ionization energy tends to increase because the electrons are pulled in closer to the nucleus. It's harder to pull them away from the nucleus because those atoms are indeed smaller. So as we get closer to 8 valence electrons, the shells become more stable, the electrons get pulled closer to the nucleus, and it's harder to remove them from the atom.